In this Flightstream tutorial, we're going to demonstrate the usage of the vortex shedding boundary condition. To begin, we are going to auto-detect our trailing edges for our model. Then we are going to select the edges of the panels that we want to make up our vortex shedding boundary condition. We're going to avoid panels that already have trailing edges defined on them, especially if we were going to create relaxed cut of trailing edges, but in this case we are working with vortex shedding. So we right-click on the trailing edge definition, go to Set Wake Type, and select Vortex Shedding, and you can see the icon changes on the left side of the definition. We'll move to setting up our solver, where we'll transfer to a turbulent viscous boundary layer model according to our Reynolds number because of the Flightstream best practices. We'll enable viscous coupling and then define our airfoil separation on our boundary. We're going to select Velarezo criterion because of the high angle of sweep at the leading edge. And now we're going to create a surface section along the span to see the vortex lift. For accurate drag calculation, we want to utilize the default pressure integration method. With this, we'll initialize the solver. Note that the vortex shedding boundary condition should only be used in the incompressible and transonic solvers. Do not use it with subsonic or modified Newtonian or tangent cone. On our surface pressure distribution, we can easily see the vortex lift due to this boundary condition that we've defined at the leading edge. And if we update our surface section, we can go to plots and see the lift visualized along the span. Now we are going to take a look at results of different aspect ratio delta wings with and without the vortex shedding boundary condition enabled within Flightstream. Beginning with an aspect ratio of 2.0, we can see that the results for the coefficient of lift when compared with experimental data are much more accurate when utilizing the vortex shedding boundary condition versus when not. We continued to get good results with an aspect ratio of 1.5. For an aspect ratio of 1.0, we have a bit more data available to us. Here we can see the lift, drag, and moment coefficients are each predicted accurately when using Flightstream with the vortex shedding boundary condition enabled. This is true over a large range of angles of attack. Finally, we move on to an aspect ratio of 0.7 where we accurately predict the lift once again. And that wraps up the tutorial for utilizing the vortex shedding boundary condition within Flightstream. Thank you for tuning in.